Now here comes the entropy part. First, let us go with the physical significance of entropy, because they might be asked for 2 marks or in a sub questions. See, physical significance is nothing but we have to compare one quantity to the another quantity. They did same here. We know that the change in the entropy of a substance is defined as a ds is equals to dq by dt. Yes. So this shows that a heat energy has a one dimension, a product of a entropy and the absolute temperature. See here, dq is equals to tds, then dq will become tds. Then next day what they did, in the earth's gravitational field, the potential energy of the body is proportional to the product of mass and its height above some zero level. So this is g. This, let us take it as a g. It has specific indications, but let's go with this. Gravitational field, the in gravitational field, the potential energy of the body is directly proportional to the product of mass. M is nothing but the mass and h is nothing but the height. So they what they did, a comparison indicates that if we regard height as a corresponding to the temperature, then height has corresponding to the temperature and a mass corresponding to the entropy. Thus, the entropy of the system is the quantity which bears heat motion. So, the entropy will bear the heat motion, whereas the mass bear the linear motion. Heat motion is nothing but the boiling water. It will boil, right? It will get heat motions. Linear motion is nothing but the like a car moving in a road with a constant speed. These all are linear motion, and this is this equation is one dimensional. So we had compared with the potential energy. You know that potential energy is also one dimensional. So physical significance is nothing but the comparing one dimensional to another dimension and giving us a physical significance. Here lastly they had concluded with quantity which bears entropy of the system is nothing but quantity which bears heat motion, and the mass of the system is nothing but the which bear linear motion. Let us begin with the entropy change in a reversible process. This is also known as a Clausius theorem. Here the first thing, most important thing is you have to remember this. See, they told a reversible cycle. Reversible cycle means if you start from one point, then you come to that point itself. So that is reversible, which can be reversible. So here is the A, B, C, D. You can see the arrow marks here. You have to mention this all the arrow marks, and most importantly this is a P versus V. P versus V graph. See, you have to remember this all. P versus V graph. Here Q amount of heat, then here Q1 amount of heat, then here Q2 amount of heat. Let us see what and all happens here. First we have to consider a reversible process of a Carnot cycle. This is a Carnot cycle as we have studied earlier in the first class itself. So this is a Carnot cycle, A, B, C, D. It is a reversible Carnot cycle. Then here the isothermal, first from A to B, here isothermal expansion takes place. Isothermal expansion takes place. It's nothing but it absorbs Q amount of heat from the source at constant temperature T1. It absorbs Q amount of heat from the source at constant temperature T1. So then we'll get the gain in the entropy from A to B is equals to Q1 by T1. So we wrote Q1 by T1. Here again they wrote Q1 is a positive because it absorbed from the system, and entropy change is a positive because temperature is a positive. Entropy change depends upon the temperature. We all know that formula, that is ds is equals to dq by dt. Here change in the entropy depends upon the temperature. So here we wrote a temperature. Then next comes B and C. Here in B and C, what happens? Here adiabatic expansions takes place. adiabatic expansions takes place. In adiabatic expansion, there will be no change in the entropy. There will be no change in entropy in a B and C. So the gain in the entropy from B to C is 0. Then next comes here isothermal expansion. Here the not expansion, it's compression. From C to D, here isothermal compressions takes place from D to C. C to D. Here isothermal compressions takes place from C to D. What happens is here Q2 it is what isothermal compression is nothing but where Q2 amount of heat is released to the sink. Q2 amount of heat is released to the sink. This is absorbed to the by the source. This is released to the sink at a constant temperature T2. This happens at the constant temperature T2. Then so they had called here loss in the entropy. Here first they called a gain in the entropy. Here we can see that there is a gain in the entropy because Q1 amount of heat is absorbed. Here we are releasing to the sink. So we wrote a loss in the entropy from C to D, that is Q2 by T1. Then next comes a D to A. Here in D to A, the adiabatic compressions takes place. Adiabatic is nothing but there is a no change in the entropy. So entropy will remain change. There will no change. Entropy will be 0. Change, if no change in the entropy means change in the entropy is 0. Then if by considering all these, then we have to get a net gain in the entropy of a working substance. So the substance working on this reversible process, its whole cycle A B C D A will be Q1 by T1 minus Q2 by T2. So when we equate a complete reversible Carnot cycle is Q1 by Q2 is equals to Q2 by T2. So when we take this to this side, we'll get equals to 0. So this is change in the, that is integration of a change in the entropy will be equals to this, and sum of Q by T will be 0. So what this says that in a reversible cycle process, the entropy change is 0. The entropy change will be 0. So in a reversible cycle, this is called Clausius theorem. After writing this, you have also write this. Here what they are telling is Q1 by T1 minus Q2 by T2 is equals to 0. What this means they are telling. So you also write this in the exam. This is nothing but we got this by the total change in the, this is a total change in the entropy of a working substances in a complete cycle. So we got this as a 0. So it in a reversible cycle is 0. Then change in the entropy combined of the combined system of source and sink is also 0. Thus the in the cycle of a reversible process, the entropy of the system remains constant or the change in the entropy of the system is 0. See what they have told here is this is nothing but the total change in the entropy of working substance of a complete cycle will be 0, and the combination of both source as well as a sink will also be 0 in the reversible process. And the cycle of a reversible process, the entropy here and only single entropy will remain constant, but the change in the entropy will be 0. You have to mention this also. See, if they ask about the entropy change in a reversible process, what and all you should consider is you have to write all those stuffs. You have to draw this first. This is nothing but the Carnot cycle. You have to mention all those stuffs which had been written in your notes. From A to B, there is isothermal expansion where Q is observed, Q amount of heat is observed at constant temperature. From B to C, there is a adiabatic expansion. There will be no entropy change. no zero entropy change. Then from C to D, there's a adiabatic compression takes place where Q2 amount of heat is released to the sink at constant temperature T2. Then from D to A, there's a adiabatic compression where there is a no change in the entropy, and you should or add all the stuffs, and you will get that the change in the entropy will be zero in the Carnot's reversible process. So this is called Clausius theorem. You should mention all these things, and it has possibility for asking 5 marks question. You will get all the 5 marks if you write all these things. Here comes the entropy change in the irreversible process. Irreversible process is nothing but where it will not meet at the point where it has initiated, so it is irreversible. So here they had considered a working substance in an engine performs an irreversible cycle of a change. You have to write this sentence. Then observing the amount of heat Q1 at temperature T1 from the source. Then next comes rejecting the quantity of heat Q2 at temperature T2 to the sink. Then the efficiency of the cycle will be given by, efficiency is nothing but eta is equals to Q1 minus Q2 by Q1, that can be written in the form of 1 minus Q2 by Q1. According to the Carnot theorem, we have studied our since our first video. Actually, first topic we had started with that Carnot's theorem. According to Carnot's theorem, efficiency of irreversible heat engine is less than the efficiency of a reversible heat engine. So at a working between a same two temperature T1 and T2, so the efficiency will be 1 minus T2 by T1. When equating this in and this equation, that is according to the Carnot's, that is greater than 1 minus T2 by T1. Now next, changing its position, this will also changes its sign. It changes to the smaller than to the greater than, has a Q1 minus Q2, because there will be, when we cancel out a 1 and 1, there will be minus. So to change the minus into positive, we have to change the sign, greater sign here. This is a, it is rule in the max. And then we'll get Q2 by Q1 is greater than T2 by T1. Then comes Q2 by equating Q2 by T2, Q1 by T2. Then here what happens, this when we take this inside, the greater than is 0. This shows that our source loses entropy. This shows that it is a positive. No, this change is a positive. So when we consider the whole system, the source loses entropy by Q1 by T1, and sink gains the entropy by Q2 by T2. See here, source will loses entropy and sink will gain entropy. What in a reversible, it was the opposite. Then the net change in the entropy for the system, whole system, will be Q2 by T2 minus Q1 by T2, and here it is greater than 0, so it is a positive. So this concludes that in increase in the entropy in all the irreversible processes, there will be increase in the entropy in all the irreversible processes, and this is known as a principle of entropy. If they ask for 2 marks, what is the principle of entropy, you have to write increase in the entropy in all the reversible process. There is an increase in the entropy in all the irreversible process. So this is the change in the entropy change in the irreversible process. This is the next one, that is a temperature entropy diagram. Here this is nothing but the diagram of a T versus S. We have seen a PV diagram, right? In PV diagram, it looks like this. We had seen this in a Carnot, auto engine, right? Auto engine, we had seen this. It is like this, but in temperature entropy diagram, it's work like this. And same way here AB will absorb the Q1 amount of heat, and the Q2 DC will release a Q2 amount of heat. Then there will be like see Q1 the amount of heat absorbed by the system along AB, here AB, then Q1 is equals to T1 delta S, T1 and delta S, it's nothing but the area. See, we multiplied the graph once graph values, then we'll get the area. So area AB EFA, this is the area. Then T1 is equals to delta S is nothing but S2 minus S1 area. Similarly, Q2 is the amount of a heat ejected to the sink along a CD. So here Q2 is equals to T2 into S1 minus S2. It is rejected, so minus. So when if we want to remove this negative sign, we have to change here S2, T2 into S2 minus S1. This is the area C, D, E, F and D. C, D, E, F and D. Here the heat energy converted into work. So work is nothing but Q1 minus Q2. When we subtract this both the areas, we'll get the area of A, B, C, D. We'll get this area. So here Q1 minus Q2 is nothing but the T2 into Q1, this equation and this equation we have to subtract. We'll get S2 minus S1 and T1 minus T2. This is nothing but the area of A, B, C, D. Then thus we know that in a reversible Carnot cycle, in a TS diagram represents useful work obtained. Here this shows that the in a TS diagram, in that reversible Carnot cycle, there is a useful work is obtained. So when we find the efficiency, when we try to find the efficiency is nothing but work done by the heat absorbed. When we multiplied this, that is this S2 minus S1 into T1 minus T2 by Q1, that is amount of heat absorbed, right? Q1 is amount of heat absorbed. Here you can see that Q1 is the amount of heat absorbed. So when we divide by this, we'll get T1 minus T2. Here we have to subtract, this will get cancelled, we'll get T1 minus T2 by T1. When you separately divide it, we'll get 1 minus T2 by T1, which is the same as obtained from a PV diagram. In PV diagram we had obtained 1 minus Q2 by Q1. Here in a TS diagram we obtained temperature, that is 1 minus T2 by T1. Let's come to the last topic, that is entropy of a perfect gas. So ಇದಂದ್ರೆ ಏನಂದ್ರೆ entropy the ಅವತಾರ ಹೆಂಗೈತಿ perfect gas ದಾಗ, ಅದೇ how it works in the perfect gas. We know that the perfect gas equation is PV is equals to nRT. When we take 1 gram of 1 gram mole, then V is nothing but the volume at a temperature P, at pressure P and a temperature T. Let us consider a system where dq amount of heat is given to the gas. dq amount of heat ನಾವು ಗ್ಯಾಸಿಗೆ ಕೊಡ್ತೀವಿ. Then according to the first law of thermodynamics, ಏನು ಹೇಳುತ್ತಂದ್ರೆ, that is dq is equals to du plus gw. Here cv ಮತ್ತು ಈಗ ನೆಕ್ಸ್ಟ್ ಏನು ಕನ್ಸಿಡರ್ ಮಾಡಬೇಕಂದ್ರೆ cv dt is a rise. cv is nothing but the specific heat of a gas at a constant volume, because cv ಅಂತಾರ. dt is a rise in temperature, dv is a change in the volume. dt ಅಂದ್ರೆ rise in temperature ಮತ್ತು dv ಅಂದ್ರೆ change in the volume. ಈಗ ಇದು ಇಂಟರ್ನಲ್ ಎನರ್ಜಿ ಏನಾಗುತ್ತಂದ್ರೆ, ಇಂಟರ್ನಲ್ ಎನರ್ಜಿ ಡಿ ಯು ಇಸ್ ಈಕ್ವಲ್ಸ್ ಟು ಸಿ ವಿ ಡಿ ಟಿ ಆಗುತ್ತೆ, ಮತ್ತು ಡಿ ಡಬ್ಲ್ಯೂ ಇಸ್ ಈಕ್ವಲ್ಸ್ ಟು ಪಿ ಡಿ ವಿ. ಇದಿಷ್ಟು ನಾವು ನೆನಪಿಟ್ಕೋಬೇಕು. ಇದನ್ನು ನಾವು ಈ ಇಕ್ವೇಷನ್ ಒಳಗೆ ಹಾಕಬೇಕು. ವೆನ್ ವಿ ಪುಟ್ ದಿಸ್ ಇನ್ ದಿಸ್ ಇಕ್ವೇಷನ್, ವಿಲ್ ಗೆಟ್ ಡಿ ಕ್ಯೂ ಇಸ್ ಈಕ್ವಲ್ಸ್ ಟು ಸಿ ವಿ ಡಿ ಟಿ ಪ್ಲಸ್ ಪಿ ಡಿ ವಿ, ದಿಸ್ ಫಾರ್ಮ್. ಈಗ we need entropy, right? Entropy is nothing but dq by dt. So we got the dq here, So S is the entropy per unit mass of a gas. S is the entropy per unit mass of a gas. So S is equals to integration of dt by t. From this we'll get 1 by t when we equate the dq values, that is cv dt plus p dv. when we do separate integration, that is the integration of cv dt by t plus integration of p by t dv. So next here there are three steps. There are three steps here. ಈಗ ಇದನ್ನ s ಏನೈತಲ್ಲ, ಇದನ್ನ s in terms of tv ಬರ್ಬೇಕು. ಒಂದೇದು first one is s in terms of tv, then second comes s in terms of tp, and third comes s in terms of a pv. We have to find these terms and we'll get the equations for a perfect gas. See, first let us consider first one, that is s in terms of t and v. Here in this equation we can see that cv dt by t pt dv. We want in terms of t and v. Here there is no problem, but here there is a problem. There is a presence of p here. We want in terms of a t. So we have to take this perfect gas equation, that is pv is equals to rt. Then we need p by t, right? The p by t ratio will be r by v. Hope you got this. Then s is equals to integration of cv dt by t plus equating this r by v dv. Integration r by v dv. Now it is easy. There is an integration, simple integration, that is cv is equals to 1 by t. Integration of 1 by x is nothing but log x. So cv is a constant, right? So it is kept constant here. 1 by t, integration of 1 by t is nothing but log e to the power t. Then here comes r is a constant. See, r is a constant. It is also known as a Maver's relations. Maver's relation is r and it is constant. Its value is a cp minus cv. This you have to remember. You should not integrate this. It is not the function. So r is kept constant. 1 by v is nothing but log v plus constant. As it is not a definite integration, we have to consider the constant here. Then comes x is equals to this same thing. We have to equate r is equals to cp minus cv log e plus constant. We get these equations. This is in the terms of a t and a v. Now the second part comes, that is s in terms of t and p. If we see this equation is in terms of, should be in terms of t and v. Here this is not at all problems, but this is also not at all problem, but here dv is there. This made us a problem. So we have to equate here in terms of p and t. So here let us consider this is again the perfect gas equation. pv is equals to rt. We have to differentiate this to get dv. If one can get the dv by differentiating, right? So we should get the equation in terms of dv, sorry, in terms of t and p, and equated with the dv. So p dv, here two variables. First is differentiated and second one is kept constant, same. Then the second one is plus, the second one is differentiated and the first one is kept the same. Plus is equal to, sorry, here it is equals to r dt. When we equate p dv is equals to r dt minus v dp, we got this equation. This is in the terms of this is in terms of p, t and p. When we equate here, that is s is equals to integration of, this is same, there is no problem in this, but this p by t we have to equate r into dt minus v dp. There might be v here, we'll solve it further. So we'll get easy calculated. So we have to keep here v. In the next steps we will eliminate it divided by t. Now we have to separate it. We have to separate it, that is integrate. This is the same here. Again we have to separate here, that is dt minus v dp by rt. When we separate here r is a common, right? So see again we know that for perfect gas pv is equals to rt. We have to equate p by rt P by RT is nothing but here comes a V, RT will be the to the denominator, then P is equals to 1 by P. So we had equated this here. This is the same, but V by RT is equated by 1 by P. Now we have to equate see, now we can see that this whole equation is in terms of P and T, so there's no problem in it. Next, this R should be equated by Cp minus Cv. When we equate this equation, don't do this this like this method each term multiplication. Do instead you keep this same here, multiply with this, then multiply with this as it is shown here. Then on a further calculations, that is Cv dt by t, Cp minus Cv dt by t minus Cp minus Cv dp by p. So here what happens next, Cv dt by t and minus Cv dt by t will get cancelled when we separate. This is kept same. When we separate these, it get cancels. Then the remaining is Cp dt by t plus Cp minus Cv dp by p. Now we have to integrate this. Integrating Cp is a constant, 1 by t, integration of 1 by t is nothing but the log t, then this is the constant, integration of a p is nothing but a log p plus constant. As this is not a definite integration, so we have to consider the constant here. And then the third part is yes in terms of P and V. First we saw in terms of TV, second TP, third PV. Here as you can see this equation is most important. You should consider this equation. Here Cp dt by t we need in terms of P and V. Here there is a dt, we have to eliminate this first part. Then here P is okay, dV is okay, but T we have to eliminate this. So what they did here is they had equated for T is in this equation. This is a perfect gas equation. In this equation they had equated for T by differentiating. Again R is a constant, don't differentiate it, R is a constant, so R they kept the same. Then PV they applied UV rule here, product rule here, you will get this equation. When we substitute dt value in this, we'll get integration of Cv, integration whole. Here Cv dt is nothing but P dV plus V into dP by R they had put, then denominator T, so dt plus P dV by T they kept this same. Again here P by T can be replaced. We know that by perfect gas equation is RT, PV is equals to RT. Here they told P by T is nothing but R by V. Substituting here R by P value where PP will get cancels. Here we have to separately divide it. When separately divided, PP will cancel dV by V and V will get cancelled dP by P plus Cp minus Cv. Here R is nothing but Cp minus Cv. Then remaining with V, that is dV by this is wrong, V. Then we'll get integration of P dP plus Cp dV by V. Here Cp Cv dV by V and minus Cv dV by V, these both will get cancelled here, so they had wrote directly. If you solve further, you will get this equation itself. On further integrating, we'll get Cv is a constant, 1 by P, integration of 1 by T is nothing but log P and Cv is the same. Then dV, integration of V is nothing but log V plus constant. As it is not a definite integration, it is, so we have to enter the constant here. See, again at the last you should consider these points, these stuffs, so that you can get the good marks out. In the above calculation, we have assumed that the entropy of a gas is a zero at a zero temperature. So entropy of a gas will be zero at a zero temperature. We had assumed that. In actual practice, however, we are concerned with the change in the entropy. In actual calculation, we are concerned with the change in entropy. So we had integrated it, right? We are concerned with the change in the entropy of a gas. When the gas changes from the state, so there will be change in the state also, like a pressure P1, volume V1, and temperature T1 to another P2, V2, and T2 respectively. This can be obtained by integrating a relation. We what and all we had derived now, all the three. Yes in terms of TV, yes in terms of TP, yes in terms of P and V. Those all we have to write here, and we'll get S2 minus S1 CV log T2 by T1, integrating with respect to T1, integrating from T1 to T2. We have to consider this, right? Then we'll get V2 by V1. Then S2 minus S1 will get T2 by T1, P2 by P1. Then S2 minus S1, P2 by P1, V2 by V1. We'll get all this. And here all the above relations stand for a unit mass of a gas, and we have to consider the unit mass here, 1 gram of a mass of gas. The entropy S and the change in the entropy is S2 minus S1 in for m grams, and the gas required can be obtained by multiplying these relation of for in with given m. To get to the required equations, we can multiply a m amount of a mass with this equation. Then we'll get the required amount of a gas of entropy. Here comes the last part of this unit, that is a third law of thermodynamics. It is known as a Nessens statement. It was given by the Nessens, so it is called Nessens statement. Here what is told, at absolute zero temperature the entropy tends to zero and molecules of the substances are a perfect order. Here at absolute zero, see the entropy is dependent on the temperature. When the temperature will become zero, the entropy also tends to zero, and the molecules in the in that substances are in a perfect order. This is the third law of thermodynamics. And the second law of thermodynamics, in terms of entropy, what it says that it states that total entropy of the system and its surrounding increases in a spontaneous process. Total entropy of the system and its surrounding will increases in spontaneous process. Spontaneous is nothing but the sudden process, where when which system sudden process occurs, there will be a total increase in the entropy of the system and its surrounding. All there will be there will be increase in the entropy. Thank you.